Hello everyone, I'm Ezgi and this is my microwave electronics term project presentation. The project is two-stage LNA design with high IP3. So throughout the design, the simulation tool Advanced Design Systems was used. The frequency band is between 4.8 to 5.3 gigahertz approximately. The source and the load resistances are both 50 ohms, and the circuit is unconditionally stable with stability factor being bigger than 1.05 at all times. The input return loss is supposed to be bigger than 7 dB and output return loss should supposed to be bigger than 15 dB. Gain variation in the band should be less than 1 dB, and overall lowest noise figure and highest gain possible was tried to be reached. This project therefore had two steps. The first one was to schematic design with ideal components, and the second one was to design the layout with lossy components. So in step one, the first thing to do was transistor DC biasing. My transistors had two gate fingers and a gate width of 100 micrometer. So for my transistors to deliver about 5.2 watts per millimeter with 3 dB gain compression, they were designed to draw 10 milliamperes. Then the stability and noise matching was done. First, the stability matching was done to ensure that this stability factor is bigger than the required criteria. Then the noise matching was done to ensure the lowest possible noise figure. It was especially important to not to add resistors at the input side of the LNA, since this will make them more noisier, and this should be avoided for an LNA. And overall, the whole circuit was merged as can be seen. The results are also shown here. S22 and S11 satisfied the criteria. However, noise figure was a little bit higher than expected, so this was tried to be reduced in the layout part of the project. And the highest gain possible is more or less was reached, since it was the highest gain possible max gain was approximately 23 dBs, and the reached gain was 22.5 dBs. So in the step two, Cree components were added. The schematic in the right was used to actually match the lamp component values with that of the Cree component, and the equations in the left was used to match them. And then this schematic with lossy components were designed. This is a big schematic, therefore I will zoom in. As you can see, additional transmission lines, pads, connectors, and three-way roads were added. Also, I had a really long transmission line in the middle of my circuit. Therefore, I kind of chopped it up into different parts so that I can swirl it in the layout to have a lower area. Also, I have added some additional components to make the noise figure less. So the layout of the circuit can be seen here. Like I said, due to a very long transmission line, the area of the LNA was bigger than expected. The x-axis in the picture is 3.2 millimeters and y-axis is 5.8 millimeters, summing up to a total area of 19 millimeters square. And the results can be seen here. The IP3 was very high. It stayed in between 29 to 30 at lower power levels, so it indicates very high linearity. The gain lowered compared to the first part, however, it stayed at a very good stage of 21 dB approximately. The noise figure was also decreased as expected. However, S11 actually passed the 7 dB requirements that it's supposed to meet. Even though it reached minus 9 dB at lower frequencies, it actually surpassed the 7 dB criterion and reached at minus 4.5. Even though it is as such for the S11, S22 stayed in between the criterion by being lower than 15 dB at all times in the band. And that is all for me. Thank you for listening.